So specific heat. Take a second to read the definition for specific heat in that document. So, what's specific heat? Don't just read it to me. Can somebody explain it? I have a beaker of water. I get 250 grams in there. What's specific heat going to tell us?
The energy required to change the temperature.
How much?
Of 1 gram.
How much temperature change? So I've got 250 grams of water. Each gram of water is going to require a certain amount of energy to raise it 1 degree Celsius. I mean, it's kind of, the definition itself kind of explains it, right? I know it's kind of, Mr. K, you're taking off the table what we would have said anyway, right? So even reading the definition, but do you understand the definition? Well, that's what we're going to do today to help drive that forward, or drive that home. If I had, good. Okay, these cylinders that I stacked up here, that's iron. That's 250 grams of iron. If I use the same amount of, or if I raise the temperature of this 250 grams of water 1 degree, that's going to take a very specific amount of energy and specific heat. These weigh 250 grams in total. If I were to raise the temperature of all of them together 1 degree Celsius, would it take the same amount of energy? So it would take the same amount of energy to raise this water 1 degree as it would to take the iron 1 degree. Yes or no? Huh. Specific heat's different for every substance. The energy that's required to raise the temperature of something, how much energy it takes to raise the temperature of an equivalent amount. Okay, in this case, our amounts measured in grams. So 1 gram of iron, 1 gram of water, they are going to require different amounts of energy to change their temperature 1 degree Celsius. It's a little close for the Bunsen burner, so I'm going to move it. So my starting temperature for this water is 27.7 degrees Celsius. What's happening to the temperature of the water right now? It's got to be increasing. Think about it. Would you put your hand over that Bunsen burner like that for very long? No. I mean, you could do that. You're not going to do it for very long, right? Because the amount of time I'm keeping my finger in the flame, yes, I am putting my finger in the flame. It's not long enough. Is it warm? Yes. I can feel the temperature in my finger rise. I'm just not going to keep it there long enough to cause me damage. Okay. So already the temperature of that beaker is up to 29, almost 30 degrees Celsius. Okay. If I put these pieces of iron on the Bunsen burner, same way I have that, the temperature of these would be much higher than what this water is right now. Because this metal takes a lot less energy to heat up than what the water does. Okay. Do we have a hot tub? Hot tubs usually have a cover on them, right? Thick, because they're insulated. Because water requires a lot of energy to change the temperature of. So the last thing you want to do is have a hot tub that you have to heat up a lot every time you want to use it. Okay. So temperature's going up. What can we say about what's happening inside this? Inside this beaker right now? What are some general statements we can say about what's happening to the molecule? Come on, go out on a limb. It's all right, safe space. Darren, you want to answer something, I can tell. Okay, so distance between molecules is what? It's expanding. Good. That's the one thing that nobody's been able, or that hasn't caught on yet today. And you bring it right off the front. Thank you. So the molecules are getting further apart. Think about it. When you heat stuff up, what does that thing do? When you heat stuff up, what does it do? It heats up. No, come on. Do I have 250 milliliters anymore? No, what do I have? Actually, no. I got more volume. Darren, you just said it. They expand, right? So when you heat things up, they get further apart. The molecules are getting further apart. Well, that means if the molecules are getting further apart, the volume here is getting larger. Now, am I losing water? Yeah. I mean, it's turning. I mean, right now it's evaporating. If I take, oh crap. I take this water and I spray it on the table, you guys at home, okay, you can't really, okay, you can't see it at home. If I just let it sit there, what's it going to do? When you come back next Friday, is that going to be there? Will it be there at the end of the period? I guess we'll find out, won't we? Will there be as much as I just squirted there at the end of the period? No, it's going to change from a liquid into a gas, but I'm not heating it up. It's just going to evaporate. It just doesn't. That's why when you get out of the pool, you don't have to towel off. You can. It helps you get dry faster, but you will eventually dry out. Right, Lindsay? You swim, don't you? Oh, I thought you swam. You what? Oh, you run. Okay. I don't have any swimmers in here. Oh, you swim? Used to? You eventually dry off though, right? Now, what else is happening? They're expanding. We're going to come back to that because that's important. What else is happening? I'm up to 86 Celsius. What's that mean? Come on, people. Darren, you going to carry us today? I can't hear you. I don't understand that statement. You can always heat up water. Yeah. I could also cool it down. What's it doing now? Cooling down. Yeah, I took the Bunsen burner out from underneath it. Okay, so it's cooling down. Okay, I'm not putting any energy into it, right? What's happening though? To go from 27.7 degrees Celsius up to, what is it doing now? Boiling. I'm right at 90. The thermometer's got a little delay in it. Thermometer says 98.7 Celsius, not Fahrenheit. Okay. Now we're at 99, 91, 99.1. Definitely at a boil. What's the temperature in there? 100 degrees Celsius. Now, we got some different things going on here. I'm just going to let it boil, but to get from 27.7 to 100 degrees Celsius, what besides the molecules expanding and getting further apart? Darren? They've got more kinetic energy, because what is temperature a measure of, class? Kinetic energy. Remember, kinetic energy is, so kinetic energy right? And temperature is a measure of the average kinetic energy. So if I said average, temperature is technically proportional. You guys have seen the squiggly equal sign before or no? Okay. So it's proportional. They're not equal. They're proportional. If the temperature goes up, the kinetic energy has gone up. What the actual numerical relationship to that is way beyond what we need to do in class, other than say, if I'm at 100 degrees Celsius, that's at a higher temperature, I'm going to have a higher average kinetic energy for the molecule. Are there molecules moving around in here that correspond to a temperature of 0 degrees Celsius? At least one? Yeah. Are there molecules moving in here that would correspond to 300 degrees Celsius? Yeah. Remember, it's an average. The average is 100. You're going to have some moving slow, you're going to have some moving fast. But the average is going to be for 100 degrees Celsius. So on average, our kinetic energy has gone up as we have done this, meaning what's happened to the molecules? They've got more kinetic energy because you've got a higher temperature. What does that mean to the molecules? Darren can't carry us all day long. I'm going to assume the people at home can hear me. Somebody from home, answer that question. If our
We
kinetic
can hear
energy,
you.
what?
We can hear you. Do I have to answer the
I
question
want
though?
you guys to answer a question. If the kinetic energy is going up, what does that mean for the molecules? And don't just say the kinetic energy's gone up. I just said that. Darren, are you going to continue to carry our sorry butts through this day? Okay, go ahead.
It's-
Where you? Oh, wait a minute. You get somebody from home to speak?
It's expanded? I think.
Well, that's what Darren said earlier. They're expanding, you get further apart. Max? They're moving faster. For our kinetic energy to go up, we have to either change the mass or the velocity. There's still water molecules. When we talk about that mass there, we're talking about the mass of the molecule, not the mass of the whole water. If I wanted to measure the mass of all the water, I'd have to throw it at somebody. Okay. So the mass of all the molecules is staying the same. They're just moving faster. So the combination of they're getting further apart, they're moving faster, allows us to get to the point where we can do what? What's happening to it? What is boiling?
The state is changing
From what to what?
from
Very good.
from a liquid to a gas.
From liquid to gas. Now, we'll talk about the term for that. You know the term for it? What's the scientific term for it? What's that? Take off the E. No. Vaporization, or they're vaporizing. So there's two different types of vaporization, boiling and evaporation. Boiling occurs at a certain temperature. Evaporation doesn't have to have a specific temperature. What's happening to the water that's on the table? It's evaporating. The temperature of the water that's on the table will not get anywhere close to the boiling point of water, yet it will still change from a liquid into a gas. The water that's in this, will it evaporate? Why? Did any of the water evaporate in the container? When they bottled it and put the cap on it, did some of the water evaporate? Okay, you're on. No, I don't want to open it up. If I open it up, sucked all the air out. Well, made it back. Well, if I sucked all the air out, you get the idea. If I took the air out, kept it back in, would any of that water evaporate? Any of that water evaporate? Yes. But it would stop because we reach a maximum up here. What would happen is we'd actually get water evaporates, but then it's also going to come back. Why does it evaporate here and dry up? Because it just goes out. It's not forced. We're not keeping it in one place. It can go anywhere within this room once it's a gas. Okay. This is going to evaporate, but it's trapped. So it can only hold so much water in that airspace. It's just going to stop. Okay, what's the temperature of this water? Come on, class. What's it doing?
100 degrees Celsius.
100
It's
degrees?
boiling.
It's been that way for a couple minutes, right? Temperature hasn't changed. I guess I should add this as liquid water, okay? So for this liquid water, I'm taking it I'm taking 250 grams of it, and I started at 27.7 degrees Celsius, and I took it up to 100 degrees Celsius. Started to boil. Do I have as much water in there now as when I started? No. The people at home would actually be able to see the difference better than you guys would, but the water level started up here. I know that thing's in the way for you guys. Started up here. Water level is now down here. I've lost already about 50 milliliters of water. I've changed, so there's 50 milliliters of water in this room now that was once in this beaker. Okay, it's a good day for moisturizing. It's so dry out. It's also why this water will evaporate more quickly now than it would be in the summertime, because the humidity in the air is really, really low. So it's going to be able to evaporate fast. Okay. So specific heat. There's a numerical value for it. So in that document, they tell you the specific heat of water is 4.184 joules over grams degrees Celsius. All right. And I'm going to make a switch in cameras because I need both boards now. Okay. What's the equation associated with specific heat? Look at the document. I mean, come on, you guys have only had to come to school twice this week. Lindsay? MC what? You don't know what the triangle is? It's a Greek letter. Do you know what the Greek letter triangle is? Bingo. You learn your Greek alphabet. Okay, so Q equals MC delta T. Heat. Where are we getting our heat from? In this demo, where are we getting our heat from? The fire. Where is that heat going? For the demonstration purposes. Into the water. Is that the only place it's going? No. it's warm up here. I turned the temperature down in the room because I was too hot teaching. So if it's a little cooler today, that's why. Because it's all about Mr. K's comfort. Okay. All right. That's going to be measured in joules. M is what? Mass. And it's going to be measured in grams. C is specific heat. There we go. Heat. A unique value for each substance. For us, water has that specific heat of 4.184. It's got weird units because it has to. You'll see why here in a second. Delta T. Delta means change in. Anytime you see a triangle in front of something in science, it means it's a change in that thing. So delta T, change in temperature. Our change in temperature is itself an equation. So we got an equation within an equation. It's temperature final minus temperature initial. That order is very important. We do not want to take the temperature initial minus the temperature final. We're looking at how is the temperature changing. So if you take the final temperature minus the initial temperature, if the temperature drops, that means your final temperature will be lower than the initial, and it will be what kind of value? What sign? If the final temperature is lower than the initial temperature, it'll be negative. Because it's lower, right? That's important. Because that's going to tell us about the heat flow. Energy flows from one thing to another. In this case, is heat flowing into the water or out of the water? Going into. What sign would we want that to be represented by? Energy going into the water. Positive. We want energy leaving the water to be negative. Okay? So we can see here that if we have a final temperature of 100 and we started at 27.7, that's going to imply a positive change in our temperature. Therefore, we have gained energy. That's what we want. So the sign's important here. All right, let's calculate how much energy did it take to get the water from 27.7 degrees to 100. It's plug and chug time. So at 250 grams, I got 4.184 joules per gram degree Celsius. And our delta T is 100 minus 27.7. Either open the app or get out the calculator. People, you can literally plug that exactly as it is written in your calculator. Parentheses, 25th, 250, parentheses, parentheses, 4.184, parentheses, parentheses, 100 minus 27.7, parentheses, enter. And you'll get the right answer. What do you get? $75,000? How much? Nope, four. Everybody all right with that? I should have asked, confirm or deny? I get several shakes or not. Okay. Is that a lot of energy? Do you even know what a lot of energy is? Does waking up in the morning take a lot of energy? I think it's more willpower than anything else. Just give you some perspective, okay? Dietary. Recommended dietary intake of calories is what? You learned this in your health class. 2,000 calories, okay? So, I've read so few. Now, the problem with this is that we're the only nation in the world that uses calories like this. Because every other nation in the world is in the metric system. This is what we call a dietary calorie. It's actually, in other countries, if you go to another country, you're going to see the energy values for the nutrition information given in kilocalories. I don't think they use joules, but I want to say that I've seen a dietary label with joules on it before. I'm not positive about that. This is a science calorie. The difference is the capital letter versus lowercase. Okay. 1 calorie is equal to 4.184 joules. I'm talking 1 science calorie, not dietary. Okay. So we're going to do a conversion here. 2,000 calories, dietary calories. Now we're going to continue the calculation, but we can get this into calories. How many kilocalories or how many calories are in a kilocalorie? What's kilo mean? Come on.
1,000.
What?
1,000.
So what am I going to have? 1,000 where?
On the top.
and that's going to be calories, and on the bottom is going to be 1 kilocalorie. So you can do it and confirm that I'm correct, but your dietary intake is not a 2,000 calorie diet. It's a 2 million calorie diet when you go with the science calories. Okay? Because remember, that's a kilocalorie. Now we're going to take it on a little bit further. We're going to go to the joules so that we can make a comparison with the same units. Okay? So I just got done telling you that 1 calorie is equal to 4.184 joules. So 1 calorie, 4.184 joules. And what do you get? Put it in scientific notation for me. Anybody?
8.368 times 10 to the 6.
So it's 8 million joules. So 8 million joules is what you, on average, dietary intake wise, what you need to maintain. This is the amount of energy required to raise the temperature of that water from 27 up to 100. Now let's just look at this part. 10 to the 4th versus 10 to the 6th. What's the difference between those? So we say 10 to the 2nd, which is how much? 100. So a little bit different in terms of the number out front, but you would be able to close with the food that you eat to maintain a 2,000 calorie diet. You would be able to heat that water up about 100 times. Your bodies require a lot of energy to live. Okay. Water. Nothing broke. Cheez-Its. You eat the whole bag, right? If you had a whole box, you probably eat the whole box. Don't eat the whole box. 1 bag is 210 calories. 10 bags would finish you for the day, right? It'd be 2,000 calories. Actually, be 2,100 calories. So, if this is how many bags of Cheez-Its it would make to get your dietary calories for the day, it would take 10 bags of this. If this can do this 100 times about, I would need 10 bags. What, 1/10 of a bag? Just a couple of chips. So relative, heating that water up, not a lot of energy. It seems like a lot because I had a Bunsen burner going forever, it seems like, right? But that's because water does require quite a bit of energy to raise the temperature. Why? Because it has such a large specific heat. Remember, 4.184. If you go, somebody go look up the specific heat of iron. I think if you just put specific heat of Fe, it'll come up as the very first thing in Google.
0.444.
0.444. So it approximately, it takes 10 times more energy to raise the temperature of 1 gram of water 1 degree Celsius than it would take to raise 1 gram of iron 1 degree Celsius. Because if it's four joules per gram degree Celsius for water and 0.4 for iron, there you go. There's your 10 times difference. It's one of the reasons why water is used as a heating source or what's called a heat sink. You heat up water when the electricity is cheap, and then the water gives off that energy after it's been heated up. Because what's happening to my water now that I've turned the Bunsen burner on? Oh, come on, seriously? I turned the Bunsen burner on. What's the water doing? It's cooling down. Oh, good job. Hey, we got more people speaking now. So if it's cooling down, where's that energy going? Out into the world. Okay. So specific heat is how much energy does it take to raise the temperature of something per degree Celsius. More specifically, how much energy per gram for each degree Celsius. Questions? Now I'm going to squeeze. When's it supposed to get above freezing? Anybody know the weather forecast? Is it this weekend?
Sunday, or yeah,
Sunday?
39 above freezing.
Okay. So Sunday is supposed to get the temperature 39. We're probably going to have a lot of flooding. I don't know. They're saying rain snow mix too. So if it rains along with all the temperature going up. Now, if the temperature gets above 0 degrees Celsius or 32 Fahrenheit, the ice is going to start melting. Where's it going to get the energy to do that? From the difference in temperature, the air. If the temperature is higher in the air, then the temperature of the ice is going to go into that to melt it. It's why once it snows, it's hard to get the temperature back up, because to get the temperature back up and melt that snow, you have to heat the snow up. And then you have to melt it. And all of those things require energy changes. Now, let's focus on the energy change that we had here. And by the way, you can see I'm at 100 degrees, 100 milliliters now. I've lost 100 milliliters, 150 milliliters of water during that process. I still have water on the table, but not as much. So even though the temperature didn't change, we were changing the state of this water. Now, what does that mean? If the temperature is not changing, what's not changing about those molecules? What's temperature measure of? Kinetic energy.
Kinetic energy.
Not changing. The kinetic energy is not changing. If the kinetic energy is not changing, what else is not changing? Darren? Yeah, we just said that. So the kinetic energy is not, if the temperature is not changing, kinetic energy is not changing. If the kinetic energy is not changing, yes, the temperature is not changing. That's Laura? The velocity is not changing. So when those molecules of water came out as from the liquid, when they came out from the liquid, were they still traveling the same speed as they were in the liquid? Yes. What's the difference? In a liquid, they're stuck in place. They're stuck in the liquid, right? They have limited movement. As a gas, they're still traveling the same speed, except they're now free to move around much more. Remember what we talked about last time in class with the states? Solids, liquids, and gases. Gases don't necessarily travel the fastest. Some of them travel the slowest. What determines the velocity is going to be what determines the velocity is going to be what temperature are you at and what mass do those molecules have. All right. Enthalpy of vaporization. Also called heat. You got it there in front of you. It's the energy required to change something from what to what. It's kind of in the name. Darren, you are carrying us today. What is it? The symbol for it is this. The enthalpy of vaporization, because your energy or the enthalpy or the heat. Enthalpy, we're not going to get into the details of it, but just think enthalpy is a way of representing energy. Okay? The symbol for it is H. Don't ask me why. So this is the enthalpy of vaporization. The units for it are joules per gram or joules per mole. We could also use kilojoules. Just depends on what units you're going to have to use. It doesn't really matter. Let's see where. The enthalpy of vaporization for water, if you look at that document, is what, 2,200 and what? 57. Now, if you look at it, the units look similar. We got the joules per gram, but we don't have the per degree Celsius. That's because the temperature is not changing here. Okay. So that's the amount of energy that's going to be required to simply change between a liquid and a gas. Now, this value will be positive if going from a liquid to a gas. It will be negative if going from a gas to a liquid. Now think about it. For us to boil away the water, we had to add energy to it, correct? Which means we want that to be a positive sign. If I have gaseous water and it condenses into a liquid, that means it's going to release energy. Okay. Now look at that number, 2,257 joules per gram. That's to change it from a liquid to a gas. How much energy did it take to heat up, change the temperature 1 degree Celsius? How much energy did it take? What's the specific heat of water? 4.184. Does it take more energy to change the temperature of the water or to change the state of the water? Change the state by a lot. A whole lot. It requires an extremely large amount of energy comparatively to change the state of something. Okay. All right. So I have 250 grams of water. If I were to boil all of that water away, how much energy would have been required? Well, we use this, the enthalpies of vaporization. We use those because there's not an equation for it. We use them as a conversion factor. And what we can say is, if the enthalpy of vaporization is 2,257 joules per gram of water, then we can say 1 gram of water, I'm going to do this way, 2,257 joules would equal 1 gram of water. Fractions like this, fractional units can be changed into a conversion factor. We saw this at the beginning of the year. Okay. So if I want to find out how much energy it took or would take to change that 250 grams from a liquid into a gas, I'd have on bottom 1 gram, and on top I would have 2,257 joules. Positive. Why? Because we're changing it from a liquid to a gas. If we were going from a gas to a liquid, what sign would I have on that 2,257? Put a negative one. And what do we equal? Remember, we were at like what, 8 million calories or 8 million joules for dietary stuff, right? So we're still able to change. with the food that you would eat, you'd still have to be able to boil away that water multiple times, about 10 times. Just to give you an idea. I said, you use a lot of energy to live. Every cell in your body is going to be converting that energy to replicate, do everything it needs to do. Although I think you guys might not be using as much energy because your brains are shut off. I'm not sure. Because that's the most energy intensive organ in your body. That's why I said feed. They tell you to feed your brain. Questions? All right. I'm done for the day. Rest of the time you can use to finish your assignments. In fact, you could probably get them done. Okay. Do the worksheet, get it uploaded, get it out of the way. Don't have to worry about it. If you want to work on the owls, work on the owls. I'll be wandering around helping you out, asking, see if you have questions. Those of you at home, you're welcome to stay if you want. If not, I'm going to go ahead and sign on. Very good.